Hello everyone, I am Ramya, Assistant Professor, EC Department from K.S. Rangasamy College of Technology. Today we are going to discuss about the topic is error detection and correction in computer networks. First we see the topic is error detection and correction. Already we know the 7 types of layer in computer networks, that is the physical layer, data link layer, network layer, transport layer, session layer, presentation layer, then application layer. So the error detection and correction is mostly occur in the second layer, that is the data link layer. If a frame is corrupted, that is the frame means it's the type of data in the second layer. The frame is corrupted between two devices or nodes. It requires to be corrected before it continues its journey to another nodes. However, the most link layer protocols simply discard the frame and let up the upper layer protocol handle the retransmission of the data. Some multimedia applications, however, try to correct the corrupted data. Next, we see the types of error. Mostly, here are the two types of errors. They are single bit error and positive error. First, we see the single bit error. The single bit error means that only one bit of given data unit is changed from 1 to 0 or 0 to 1. The single bit errors are the least likely type of error in serial data communications. The type 2 is positive error. It means that two or more bits in the data unit have changed from 1 to 0 or 0 to 1. A positive error does not necessarily mean that the errors occur in consecutive bits. The length of the burst is measured from the first corrupted bit to the last corrupted bit. Some bits in between may not have been corrupted. Here see the examples of single bit error. Here in center side we have a 8-bit data, that's the frame 10110011. It is sent to the receiver. We got the data is 10110111. Here the third bit is corrupted. Here the only one bit is changed. So that is the single bit error. Next example for first error. Here the same input data in the center side, it is sent to the receiver part. Here see the differences. In receiver part 11000111. Here the 3 bits are changed. So here the number of bits is increased. Next one is the redundancy. The central concept in detecting or correcting errors is redundancy. To be able to detect or correct errors, we need to send some extra bits with our input data. These redundant bits are added by the center and removed by the receiver side. Their presence allows to the receiver to detect or correct corrected bits. Here the 4 types of redundancy is used in the data communication. There are VRC, LRC, CRC checksum. Now we discuss about the CRC, cyclic redundancy check. The cyclic, first we see the cyclic codes. In a cyclic code, if a code word is cyclic shifted, that is rotated, the result is another code word. For example, if 10110000 is a code word and we cyclically left shift, then the output is 0110001 is also act as a code word. Here see the some data example for some data word and the code word. So here see we can create cyclic code to correct errors. For example, CRC code with C of 7, 4. Here the data word is 4 bit is 0. The code word is 8 bit 0. Next 001 means 001. The code word is 0111. Next 0010. The code word 0010110. So like that. So the data word is 41. The code word is 8 ones. Next, here's the encoder and decoder. It's the one error correction and detection process in the data link layer. First, see the center side. It's the left hand side is a center port. Here we using the encode process. Here we have the data word A0 to A3. So totally have a 4-bit data. Then here is the 3 bits are the redundancy bit, the additional bits 0. Here it goes to the generated block. Then we apply the division methods. Finally we got the code word. Here the code word means data word plus remainder values. Here the remainder value is R0, R1, R2. It's the actual code word in the center part. Next, in unreliable transmissions, here using the 4-bit divisor D0 to D3. Here, next we move to the receiver part. Here see the decode process. Here the code word is same. Here the B0 to B3 and the quotient Q0 to Q2. Here also the 7-bit data. It goes to the checker. Here using the same division method. Here using the syntrom. Here's the error correction detection part. It is the remainder part. Here the remainder value is 0 mean it is accept the data word, original data word. Otherwise, it is discarded. Here the decision logic is the data word is accepted or either discarded. So it is based on the remainder values. The remainder value is 0 mean the data is accepted. The remainder value is non-zero mean it's discarded. Here the expansion of the previous slide. Here the encode the data word K as assume take the K bits. So here see the 4 bits. It's the represented by K. Next, the code word has n bit. That's totally 7. The size of the data word is augmented by adding n minus k 3. So 3 right hand side of the word. In n bit, result is fed into the generator. The generator uses divisor size n minus k plus 1. That's the 4-bit divisor. It's the 4-bit divisor. The predefined and agreed upon, the generator divides the augmented data word by the divisor mod to division. The quotient of the division is discarded. The remainder is appended to the data word to create the code word. Next, the receiver side, the decoder receives the possibly corrupted code word. A copy of all n bits is fed to the checker, which is replica of the generator. So the remainder produced by the checker is a syndrome. N minus k, so 3 bits. This syndrome is produced the 3 bits. Bits is fed to the decision logic analysis. The logic analysis has simple function. If the syndrome bits all zeros, the 4 leftmost bits of the code word are accepted. That's the original data word is accepted. Here we assume interpreted as a no error. Otherwise, the 4 bits are discarded. Here we occurring the error. Next, see the division process in the CRC encoder. The data word is 1001. The divisor is 1011. Using up then we have add the redundancy bit 000. So we are using totally 7 bits code word. Here using the division method, the leftmost bit is 0 mean use 4-bit divisor. Here we apply the same division process. Here the remainder value is 110. So in center side the encoder, the code word is original data word plus the remainder value 3 bit. So original data word is 1001. The redundancy bit is replaced by the remainder value. So 00 is replaced by 110. It's the center port CRC division process. Next, the same code word is sent to the receiver port. Here we see the decoding part. The same division, the code word input is original data word plus the previous remainder value. Here applying the same division process, the LSB 0 mean we are adding the 4-bit division 0. Here following the same procedure, finally the syndrome, that is the remainder value is 0. The all 3 bits are 0. So what's the condition? Syndrome's all bits is 0 mean it is no error. So the original data word is accepted. So the data word accepted. The original data is 1001. The leftmost 4 bits. Another one, in case the data code word, the input code word is error is occur mean, for example, here see The code word is 1000 1 and 0. So the original data word, the single bit is changed, we assume. So using the same procedure for the division here, following the same, here the syndrome base is non-zero. So that is 0 1 1. So the syndrome base is non-zero mean the original data word is discarded. So we assume here the error is occurred. Next one is the using polynomials. We can use a polynomial to represent a binary word. Here each bit from right to left is mapped onto a power term. That's the degree, polynomial degree. The rightmost bit represents the 0 power term. The bit next to it to 1 power term extra. If the bit is of value 0, the power term is deleted from the expressions. Here see some polynomial to represent a binary words. For one example, 11000001, that is A0 to A6. It's how to convert the polynomial term. Here the first bit A1. So A0 value is 1. 1 into x power 0. Next 1 into x power 1. Next 0 is A2 into x power 2. A3 0 into x3. Fourth 0 into x4. Fifth also 0 into x5. The last A6 1. So 180 x6. The highest degree of the polynomial is 6 here. So it's how to short form it. This binary value is converted to polynomial equations 1 plus x power 6. So the remaining 0 bits are power term is deleted from the expression. Next, same CRC division using the polynomials. Here input as a polynomial equations. So now we need to convert the binary terms, then follow the same CRC procedure. Otherwise, you division the same. X3 plus x1 is the division. Here is the code word. Here also using the reductancy data. Here the original data word x3 plus 1. Here using the polynomial, here see the remainder values. Here the code word is data word plus remainder values. If the generator has more than one term and the coefficient of x power 0 is 1, all singular exponent parts. Here are some standard polynomials for our examples. Here name CRC8. It's the polynomial expression for CRC8. The application is ATM header. The CRC10. CRC10 means the highest polynomial degree is 10. X power 10 plus x power 9 plus x power 5 plus x power 4 plus x power 2 plus 1. Here's the ATM. Application is the ATM AL adaptation layer. CRC6 mostly used in the application of HDLC. CRC32 is used for the LAN functions. So today we see about the error detection correction in the data link layers, how to process the CRC in encoder and receiver side, some polynomial equations. Thank you.